All right. We are at episode 3 of Analysis with Friends. I think that's what I titled the series.
Yeah.
And so let's just do, you can definitely click on the previous video, but as a very quick recap of where we got last time, we talked about, I'll just scroll up. I have some of those notes. We talked about limits of sequences. We formally proved that the limit of the constant sequence is just the constant that determines it. And we also made an investigation of this sequence of 1 over n, and in fact, we formally proved that the limit of the sequence where the nth term is 1 over n converges to 0. And sort of a thing we left off on was saying about how today we were going to talk about sums of limits and comparing them. So just want to toss that out there as a quick reminder, which we're going to come to in a moment. But right before we began recording, Stephen, you were telling me about how you're feeling pretty comfortable with the definition of a limit. And I asked you, is that the limit of a sequence or the limit of a function?
Yes. And it seems that I might have confused them because they look similar. Am I wrong that they look similar?
They definitely look similar. They definitely look similar, but they're different in important ways. I mean, to be fair, we did say in the first video that a sequence, one way to define a sequence is as a function from the natural numbers to the reals, but that is a very different thing than a function from the real numbers into the reals, or the rationals, if you will, because we're sort of pretending the reals haven't been invented yet. So maybe we can start off. Maybe you can tell me your definition of a limit. The one you're thinking of right now that's on the top of your mind. We'll see which one that is.
Right. So for all epsilon greater than 0, there exists an n in the natural numbers
Yeah.
such that little n is, what is it, greater than or equal to big N?
Mhm.
Less than or equal to, or is it's greater than? Okay, good.
Yeah.
Big N. Um, and then there's the absolute value of a sub n minus L that's greater than epsilon.
Greater than?
Less than epsilon, sorry. Yes.
Yeah. It's important to remember, it's one thing to memorize which way the symbols go, but it's even more helpful if you remember the idea, right? We're
Right.
trying to make the a sub n really close to L. So we want to make their distance less than any positive number.
Right. It needs to be less than epsilon
Yeah.
because you give me any epsilon and I'll find an n that fits inside the neighborhood. Right? Is that the correct way to describe that?
Well, this is so the a sub n will be in the epsilon neighborhood of
Yes.
L. That is there is some terminology there to describe that. Yes.
The epsilon neighborhood of L, where we have L in the middle and then minus epsilon and plus epsilon to either side of L.
Yes. So let's maybe take a second to unpack that for people who might be following along with the series, because it sounds like you've been doing some reading on your own, and maybe some people who are following along with this haven't seen that terminology about neighborhoods just yet. So this is the definition of a limit of a sequence, right? So if this is true, then we would say that the limit as n goes to infinity of the sequence a sub n is equal to L. Yeah. So just for the readers at home, let's talk about neighborhoods for a moment. So given any epsilon greater than 0 and say x, some real number, or let's keep with this. We haven't invented the real numbers yet. Although, again, all of these definitions work just as well whether you're doing real or rationals, but we're making our way to the construction of real numbers. So given any, just to highlight this, epsilon, I'm going to write q plus. So by this, I mean positive rational number. Given any epsilon and any x, a rational number, the epsilon neighborhood around, or maybe we would say about x, sometimes denoted b epsilon x, this is defined to be, right, by definition, this is simply the set of all of those points in the rational numbers whose distance away from x is strictly less than epsilon. So this is the epsilon neighborhood, or we might sometimes call it the epsilon ball. And this actually has a generalization to multiple dimensions. But if we just think about drawing this on the line, right? So we take all of our rational numbers, we put 0 here, we put -1 here, we put 1 here, etc., etc. So if we just think about drawing this line representing all of our rational numbers, then what does this look like geometrically? Well, if, say, our point x was here, then the epsilon ball, so I'm going to make a curly brace here, a curly brace here to mean that the points exactly at x plus epsilon and x minus epsilon, these are the endpoints, they are not included, right? Because those do not have a distance strictly less than epsilon. But everything else in orange would be included.
And our y, where does our y show up on this line here? Because we're
right. So x is the point determining the center, right? And the y's, right? There could be lots of different y's in this set. So we're saying find any y that you possibly can that satisfies this condition that its distance from x is less than epsilon, strictly less than epsilon. And if you have such a y, boom, that's going to be in the set. So everything in orange here essentially is going to be some possible y.
okay.
Right? Because anything to the left of this rightermost brace and everything to the right of this leftmost brace, those are exactly all the numbers that have distance less than epsilon away from y.
Right. That makes total sense.
Yeah. And so this actually gives us a new way to write the definition of a limit. We can sort of write it in a slightly different notation if you want. There are times when this could be a convenient way to write things, because notice L is sort of some fixed point, right? And we're saying in our definition that for any epsilon, there exists an n such that for little n big enough, all of those little n, well, if we look at the definition here, and you look at the definition here, this is exactly saying that the a sub n are in the epsilon neighborhood of L. Technically, because now it doesn't actually matter all that much, but because I've written the x on the left, if we remember that the absolute value of minus x is the same thing as the absolute value of x, we have that the a sub n minus L is the same as L minus a sub n, and now we see it lines up exactly with the x being L. So just in other words, to rephrase this a bit, another way we could write the definition is for all epsilon bigger than 0, there exists a big N in N such that little n is bigger than n, it forces a sub n to be in the epsilon neighborhood around L. Right? So in other words, it says eventually all of your points end up in that epsilon neighborhood, no matter what neighborhood that is.
Mm-hmm.
Yeah.
I think the one thing that was the most challenging for me is just trying to wrap my head around the relationship between little n and big N, because we need to find an nth term in our sequence that needs to be sufficiently high in order to find its place within this epsilon neighborhood.
Right.
And I'm not sure what it is about it, but I'm looking at n greater than or equal to big N, and I'm looking at a sub n, and for some reason things are just not clicking in my mind. So I'm wondering if there's a way that we could further visualize this, perhaps. I'm not sure what we need to do to make sense of this in my mind, but I'm struggling with it.
Well, because the way it's written right now is very abstract, right? Because it's saying that we can play this game for any epsilon. And we're saying eventually, right, all the n past some point will make it such that everything's eventually in that epsilon neighborhood. But let's first let's look at a stupid example, because those are the best ones to start with. Let's return to our constant sequence where a sub n is just equal to 1 for all n and n, right? So as we've seen, this is the constant sequence of ones. The limit of this sequence is just itself equal to 1, right?
Mm-hmm.
So what does that look like? Well, if we, we take our line of rational numbers, here's 0, here's our point 1. So what are we saying? We're saying that, well, pick an epsilon, right? I don't know, pick any epsilon you want. Some number. Make it small.
Should it? Okay. Does that mean?
Or it could be huge. It doesn't matter. It could be 10 billion. It could be, right? Because what does our definition say? It says for any epsilon, for any positive epsilon, this stuff is going to happen, right?
Right. So maybe 100.
100. Sure. Okay. That's huge, right? So I'm not drawing this to scale, but maybe 100's out here. So, well, this would be 101. And here would be minus 99, right? So 100 distance in either direction. And this is the epsilon ball around 1 would be this, all of these numbers, right? And what's this saying, right? If it's true that this limit holds, that means, okay, for this epsilon, right, we've just drawn a picture here of the 100 ball centered at 1. And if indeed this limit is what I say it is, then you need to convince me that eventually, every term in this sequence lies inside this epsilon ball. Is that true?
It is true.
It is true, right? Because every single point in the sequence is literally the center of this epsilon ball, right? So there's nothing to show really. I mean, you can show that this holds by letting n be equal to 1 itself, right? Because of course it holds for all indices. But it's also true for n equals 100, right? That's all you need to say is just at some point, all the little n that are bigger than or equal to 100 if I take a sub n, it'll land somewhere in here.
Sure.
Yeah.
Also, from the text that I'm reading, I don't know if this is the same, but when we said the simple or dumb case, is there a terminological difference between solving the base case and this, or is this a base case example?
Well, base case can be used in a number of different ways in mathematics, right? So I don't know if you've come across the principle of induction yet in your readings, but the base case often comes up in something like the principle of mathematical induction. So that often describes, some sort of fundamental case. I wouldn't really call the constant sequence a base case here, although it certainly is a very basic sequence or fact that you would really hope is true if you're going to, accurately capture this idea of sequences and whatnot.
Sure. So in my observations, looking at various texts and lectures on this subject, it almost seems to me as though there is some sort of hit and miss or some trial and error that takes place. There's a way to, so it is kind of a trial and error process to determine this particular set of n, this big N, right?
And as we've seen, it's not like there's just one answer, right? In this case, we could have taken big N to be equal to 1 or big N being equal to 100, right? It doesn't matter, right? What it says in the statement here is there exists, right? So you just need to convince me that there's at least one N so that everything past that N makes the statement work, right? Because all we really care about is eventually the terms are epsilon close to L. That eventually could be at 40 million billion, right?
Yeah.
So imagine, like, for instance, to give you an example, maybe my sequence is this, right? So maybe I have a sequence B sub n, and I'm going to define it like this. So B sub n will be equal to negative 99 for all n between 1 and 10 to the power of 80, which is about how many atoms are in the observable universe, right? That's big. You're never going to count that far. Like, you'll never, even the fastest computer on the planet will never, going one by one, it'll never count up to 10 to the 80, right? It's just an insane number. So this number is already way beyond what humans can even fathom. Like, we can't even really, no one can really fathom the size of the Earth, for example. And the number of atoms in the Earth pales in comparison to 10 to the 80, right? It's nothing close. I don't know the exact number, but it's nothing close to this, right? We already can't, you can't actually comprehend something of that magnitude, right? And this number is way beyond that. So the first 10 to the 80 terms of this sequence are 99. And then I'm going to say that the rest of the sequence is just 1. For the rest of everything afterwards. Well, the limit of this sequence, right? The limit of the sequence is still just 1.
Right.
Even though all this crazy, like, completely different number is happening for an inconceivable amount of positions before we hit some point, eventually everything is just 1.
And so there's another thought that I'm having, because if we're saying that it's convergent, the epsilon neighborhood, say we were just to take one side of the epsilon neighborhood, it's yay big, and then we make it smaller, right? And we can make it smaller and smaller and smaller.
Yes.
This indicates that there are infinitely many epsilon that are there infinitely many epsilon that satisfy this? Well, there are infinitely many big N that you could put into this that would satisfy, right?
Well, what we're demanding, what we're asking for in this definition is that this be true for infinitely many epsilon, right? We're saying that this needs to hold for any epsilon bigger than 0. You need to convince me that no matter how small you make epsilon, they'll always be, eventually, all of the terms will be in that epsilon ball, no matter how small you make it.
And so if I'm thinking linearly here,
Mhm.
so we usually plot our lines left to right, and then we hit our limit, and then we have this whole other plus epsilon side of it. So
Ah,
we're talking about reaching a limit, but we're also talking about this area beyond the limit, which is running counterintuitive to my
right.
intuitions, we'll say.
But the thing is, the reason why we have both sides of the epsilon is that our sequence doesn't need to just increase or decrease. And this actually leads us to an important definition, which I'll talk about in a second, but an important concept of a monotonic sequence or monotonicity. So, well, let me just define it first, and then I'll explain why this definition matters, right? So a sequence, a monotonic sequence sequence is one for which a sub n is less than, or let me say it this way. One of two things can happen, right? So if little n is less than little m, then that means that a sub n is less than less than or equal to a sub m. So this would be a monotonically increasing sequence, right? As you go further along the sequence, your terms get bigger, or at least they stay the same, right? So for
Right.
example, our constant sequence is monotonic, right? Because it stays the same. The sequence that goes 1, 2, 2, 3, 3, 3, 4, and so on. This is monotonic because it increases sometimes it stays the same, but it definitely never decreases the further you go, right? So
Okay.
these are both examples of monotonically increasing sequences. Here's a non-example: 1, -1, 1, -1, and so on forever, right? That is not monotonically increasing. So this would be monotonically increasing. And, well, what do you think it would be? What do you think it should mean if the function, if it's monotonically decreasing? What
Is this
symbol
like
should I put in between these?
uh well greater than or equal to in this
Yeah,
case?
exactly. So it just says in this case now things are decreasing, right? So for example, our sequence 1, 1/2, 1/3, 1/4, right? That this is a monotonically decreasing sequence of numbers.
Okay.
Yeah.
And
And it,
so when we say monotonic, it just means that we're either increasing or decreasing, and it's not a combination of both.
yes, exactly. So
Okay.
it could also just be staying the same, right?
Right.
Because remember, these, like a sequence, a constant sequence is both monotonically increasing and decreasing, right? It satisfies both properties, right? It's just saying it's so monotonically increasing means it's just definitely not getting smaller. It could get bigger sometimes, right? Like in this one here, but not every jump actually gets bigger, right? Like we have
Sure.
some places where it's 3 and then it's 3 again. But as long as it's not getting smaller ever, then it's monotonically increasing.
Maintains the overall same trajectory.
Yeah.
Okay.
Yeah.
And just because I'm very curious with language, what is the relevance of the term tonic in this case? Why do we call it tonicity of
And
some kind?
I know you're asking because you are a music theory buff, and of course the tonic note and the tonic chord is very important to you. Um,
Yeah.
to be honest, I don't know. Mono mono is means same or single, right? Mono, one. So one direction. I would assume that tonic, I'm not that great at Latin, so I would imagine that it comes from some sort of Latin root of a word related to direction. That would be my guess, but I don't know. So a fun thing for everyone to Google before the next episode.
Sure thing. I'll be doing it too. You can bet.
Right. Great. So good. That was a great question because it led to an important definition. But setting that aside, let's return to this question. So not every sequence is monotonic, right? For instance, we saw this one is not monotonic. Well, it's not a convergent sequence. We could probably prove this formally. That's a good homework exercise, although it's it can be difficult to prove that a sequence doesn't converge ever to anything. But let's look at an example of a sequence that is not monotonic and does converge. And it's going to be very closely related to a sequence we've already seen. So here's the sequence. I'm going to define it as C sub n, and I'm going to define it as -1 to the power of n divided by n. So let's write out a few of these terms, and then let's draw a picture of what's happening.
Cool.
Right? So I'm going to actually, maybe instead of just erasing it, maybe I can just shift our monotonic definition down screen a little bit and give us some more space. Perfect. So let's write out a couple terms of our sequence, right? So C sub 1, this is -1 to the power of 1 divided by 1, which is?
Just one.
Careful. -1 to the power of 1 is?
Just -1?
Just -1. Yeah.
Yes.
So
-1 over 1.
Yeah, which works out to be -1. Okay.
It's these little things.
C2 is -1 squared divided by 2.
So that's 1 over 2. So that's 1/2, right?
Yeah, that's +1/2.
Yeah.
C3 is going to be -1 to the 3 over 3.
So that's -1/3.
Yes. And just for good measure, let's do C4.
+1/4.
Exactly.
Right.
Right. So it's the sequence that we've seen before, right? 1 over n, but now the sign is alternating each time instead of just, so this is not a monotonic sequence, right? Because we're flipping back and forth constantly between positive and negative numbers. And so let's draw a picture of this, right? Well, let me maybe ask you, what's your guess for what this sequence converges to?
I think it converges to 0.
Yes. So it also converges to 0, right? Also converges to 0. So here's our point 0 in the middle. And I'm going to draw things really, really big, right? So maybe over here is 1, right? And over here is -1, right?
Sure.
And let's draw some of the terms in our sequence then. So we might have something like, so the first term in our sequence is -1, right? It's over here, -1. And then the next one is 1/2. And then we have 1/3. And then we have, or -1/3, I should say. And then we have -1/4 and -1/5, I might be getting the order.
You
right?
are correct.
So they're going right on either side like this, right? And so this is why we need both sides of that epsilon neighborhood, right? Because it's not true, right? If I just looked at, say, the left side of this epsilon neighborhood of 0, well, it's not true that all of my terms are eventually in this left side neighborhood, right? I have this whole infinite number of terms that are going to be on the right-hand side, namely all of those even indexed terms, right? Those are all going to be small positive numbers close to 0. And so if my definition of a limit only included one side of this epsilon neighborhood, then it wouldn't be true that this thing converges to 0, right? But that wouldn't be a very good definition of limit, because we can see from this picture, as we're drawing things out, we can see that the points are getting closer and closer to 0, right? So that's exactly the reason why we have in our definition, in the original definition of convergence here, that's really why we have an absolute value bar here, instead of just saying a sub n minus L or L minus a sub n, because things can bounce around on either side. And we don't care about that, right? We care about, so we want to allow for the possibility that things sort of wiggle from the left or to the right, as long as the very long-term behavior is to get as close as possible to that single point.
Right. It's going to converge. And so this is another way of looking at the visual. When you said we were going to draw it, I was visualizing the x-axis and we were going to go continuously to the right like a typical number line, but we converge to it as if we were on the x-axis, almost as if like these were our red y-axis dots. Do you know what I'm saying? Like we'd have y and then we'd have x running like normal, and we'd have one that would be higher than x, the x-axis, and then lower and then higher and lower, and we'd slowly get closer to the x-axis. But now we're visualizing it like on the line.
Yeah. That's another way. That's another way we can write it too, right? So if we wanted, we could consider our whole totality of rational numbers going up this way, and we could consider, an axis here, but we don't really want to think about this as a line, right? Because here, this is indexed by natural numbers. So we would only put like 1, 2, 3, 4, 5, 6, etc. And yeah, you're right, though. In the same case, here's what would happen, right? So 1 would be -1, 2 would be, positive 1/2, 3 would be negative 1/3, and then positive 1/4, and then like this, right? And so, of course, as we keep going down the line, these get closer and closer to here, but we're allowing for that possibility that they jump around a little bit, as long as they eventually wiggle their way down to 0.
Certainly.
Yeah.
And so when we were using the other example, was that technically a line then, or are we still not calling that a line with the epsilon neighborhood that we were showing before?
Which
in your example here.
Yeah.
So this is technically a line, right? But what we just did before, you were saying that wasn't
like
technically
this thing,
a line.
Q is a line. Yeah.
But in our other case down below, we were saying that was a sequence. So really, we were only considering or interested in these particular natural numbers.
Yeah, I mean, here we're only considering the natural numbers, right? Because it's some sequence. Yeah.
Okay.
Yeah.
Just clarifying.
Yeah. Okay. So, yeah. So I want to come back now to our original goal for this episode, and that was to talk about sums of sequences, and figuring out, because we might think to ourselves, let's come back to these sequences, the constant sequence and the sequence of 1 over n, right? And I mean, one way to, for example, to build up more complicated numbers, right, from simpler numbers is to add them together or multiply them together or divide them or etc. We can do different operations on numbers. And since
Sure.
sequences are built out of numbers, we might hope that a more complicated sequence, we would be able to sort of break that down into simpler sequences and use properties of addition and subtraction and multiplication to figure out what's going on with our more complicated sequence. So for example, I could consider the sequence C sub n, which is 1 plus 1 over n, right?
Hmm.
Well, this sequence, as you can see, obviously, it's the nth term of the sequence C is just the sum of the nth term of the sequence A and the nth term of the sequence B. And so maybe there's a way we can leverage those properties instead of having to, prove from scratch. Again, I mean, we know what A sub n converges to, right? And we
It's
know that,
0.
and A sub n,
Oh, sorry. A sub n converges to 1
yes,
and B sub n to 0.
yeah.
Looked off the
So
page.
we might hope that instead of pretending like C sub n is some totally new sequence we've never seen before in our lives, and we have to start from scratch, proving what it converges to, well, we might hope that somehow, because of its relationship with A sub n and B sub n, that we could, have an easier time proving what its limit would be. Right? I mean, what do you think 1 plus 1 over n is going to go to as n goes to infinity?
It's hard to imagine, but it's 1 plus 0, so it must converge to 1 because one part of our function, our limit, in that case, is converging to 0. So it eventually, I guess, the long-term behavior of that sequence has no bearing on it because it converges to 0.
Exactly, right? So in other words, the guess is this. The limit of the sequence defined by A sub n plus B sub n, more generally, much more generally than these specific examples, we should expect that this should be the same thing as simply taking the limit of either of those two sequences and adding up those limits, right? Seems like a reasonable thing that should be true.
Yeah.
Of course, as mathematicians, we don't want to just call it a day and say, well, you know what, that seems like a reasonable thing that's true, so I'm going to stop thinking about it at this point. Right?
Yeah.
No, we want the proof. We want to know that it's true. Okay, so now we begin the hunt for the proof. So how could I prove over here, right? I'm trying to prove that the limit of some sequence is equal to something, right? I mean, in some sense, this is my L, if you will, right?
Mm-hmm.
So maybe I could even a more compact way to write this would be, if I'm calling this L and I'm calling this M, I'm trying to prove that this sequence converges to L plus M.
Right.
Right? So what does our definition say? How do I start writing out my definition of a limit? What would that say? What am I trying to prove here?
Well, we're still trying to determine that for an epsilon, for all epsilon,
For all epsilon greater than 0,
right? There exists an n in the natural numbers
yep,
such that little n is greater than or equal to big N.
Would imply that,
Now we have to get L plus M in there somehow.
yeah.
They're right. Is
Well,
it just
first off, we write what our sequence would be, right? So our sequence, right? The nth term of our sequence is a sub n plus b sub n minus, and what's the thing that we think it's going to converge to?
1?
Hang on. Let me actually say this. Forget about our specific example now. We're going to
Okay,
try and dive into the abstraction. So
sure.
forget that I said that a sub n is this sequence and b sub n is this sequence. We're going to try and prove this for arbitrary sequences. So I'm saying take any sequence a sub n that converges to a sub l, so that's important. Built into this is the assumption that I'm working with a convergent sequence. So I don't want to take something like 1 minus 1, 1 minus 1, 1 minus 1.
Right.
And take a second sequence b sub n that we are assuming, we're baking this into the assumption of the problem, that it is m. So what is the thing that we think the sequence of terms a sub n plus b sub n is converging to?
We can just drop that L plus M right in there, right?
Yes, exactly. And we want that to be less than epsilon. Right. So we're not going to be able to just write the proof right off the bat, right? Because here's not how mathematics works, right? Here's the way it doesn't work. You don't just sit at a paper and stare really hard at it until suddenly you see the entire proof in your head and you have the idea and you just start writing away. That is not what happens. Mathematics is a messy, dirty process of experimentation and notes and playing around and fudging around, right?
Mm-hmm.
So why don't and here's the way that, especially in analysis, oftentimes here's how proofs go. We need to figure out how to cook up this n, right? This recipe based off of any epsilon that we can possibly find, right? So sometimes it can be helpful if we work backwards from this statement.
Okay.
Right? And remember, let me give you some hints here. Here's some things that we do know are possible, right? We do know, because we're assuming that the limit, we're assuming that the limit of a sub n is L. We do know it's possible that for all epsilon prime, just to give it a slightly different name, right? To not confuse it, it might not be the same epsilon here. We know that for all epsilon prime, there exists an n prime such that if little n is bigger than or equal to n prime, then it has to be the case that a sub n minus L is less than or equal to epsilon prime.
Right. So we're taking part of our greater definition and we're breaking it now down into two definitions.
Right.
Is that what I'm gathering here? Okay.
Yeah.
So
I
the
mean,
one of them for
this is part of our assumption, right? We're saying, to start off with, assume I have a sequence a sub n that converges to L, and assume I have a sequence b sub n that converges to M.
Sure.
And assuming that, I want to prove under that assumption what the limit of this other sequence is. Well, let's unfold those parts of the assumption that we're working with, because maybe those are useful tools, right? So I know I can get these two things, M. So the goal, what we would like to try and do now is take this thing, take this expression, see if we can rewrite it somehow and hopefully rewrite it in a way that we might be able to make use of these pieces of information. And my one other hint to you is the triangle inequality.
Right. So we can take the absolute value of a sub n minus L
Yep.
plus the absolute value of b sub n minus M.
Yep.
And would
And what relation does that have to the thing on the left?
Is, are we saying less than epsilon? No. What are we doing here?
So sorry, finish what you were going to say first.
Well, that's where my brain went to put that together, and that's just kind of as far as I've got.
Right.
And now we
So
need something else.
How would you repurpose this in terms of the triangle inequality? The triangle inequality relates this to something else, right?
Mm-hmm.
So where does the inequality go, and what's the thing it relates it to?
Trying to remember if it's greater than or equal to. It's
so
is it greater than or equal to?
The triangle inequality says that x plus y is less than or equal to the absolute value of x plus the absolute value of y.
Right. Of course. Yeah. It shouldn't be greater. Yeah.
Uh-huh.
Okay. And so then we need to have less than or equal to after this two clauses, I guess.
So wait, I'm putting it here.
Oh, in between. Sorry. Yeah. We're going to put it right between these two here. Yeah.
Yes, exactly. Okay. And okay, I know something about a sub n minus L, and I know something about b sub n minus M, right?
They're less than epsilon.
Well, one of them's less than epsilon prime, one of them's less than epsilon double prime.
Right.
Right. So what could I say about their sum? It's less than
2 over epsilon, or like the sum of the two of them.
Yeah.
Oh, so like 2 epsilon.
Well, careful. So if I knew that x was less than 2 and y was less than 5, then x plus y I could say is less than
7,
right? So 2 plus 5.
Oh, so it's epsilon plus, or epsilon primed plus epsilon double primed?
Yes.
Specifically? Okay,
yes.
Right, because they could be different and
yes.
they are denoted as different. Okay.
Yeah. They're
Gotcha.
denoted as different because they could be different. They could be the same. We don't know. They're just,
which is,
yeah.
Right. Which is why we can't just go 2 epsilon and call it a day.
Right.
Okay.
So here's the thing, right? Ultimately, remember our goal in the purple here is to make a sub n plus b sub n minus L plus M less than epsilon, right?
Mm-hmm.
Well, if we could make this, thing equal to epsilon, then we would be done, right? Because here we have a sub n plus b sub n minus L plus M.
Mm-hmm.
We can use the triangle inequality, which is always true, to get this, from which whatever our epsilon prime or epsilon double prime is, if we can pick them to be such that their sum is epsilon, then we'll have done it, right? We'll have gotten this term to be less than epsilon, our arbitrarily chosen epsilon.
Okay.
So here's this could be a little tricky. I don't know, maybe not. How could I write how could I write this? Well, let me say this, right? Because we're assuming that the limit of ace of n is L, I mean, we're assuming that this is true, right?
Yep.
So that says, hey, you're allowed to take any epsilon prime bigger than 0, and I'm guaranteeing you that I will find an n that makes that work. I'm guaranteeing it.
Right. So we can just choose one.
We could just choose one, right? Same thing with epsilon double prime. So we can choose them basically to be whatever any positive numbers we want. So what could we pick epsilon prime and epsilon double prime to be so that their sum is epsilon?
You can just pick two numbers, right? Oh, well, do they need to be the same number?
They don't necessarily need to be. It might be nice if they were.
Right. Okay. So maybe 4 and 4.
But remember, we need to make this recipe work for any epsilon, right? So if I pick 4 and 4, is that guaranteed to be equal to?
Oh, no, right. So 2
Oh,
over epsilon, maybe.
you're close. You're close. But so 2 over epsilon plus 2 over
Oh,
epsilon.
it's the same thing. Oh, epsilon over 2. It's like
Yes.
half an epsilon, right? Okay,
Yes,
yes.
you got it. You got it, right? So if I can choose, right, by definition, I know I can always find some n prime to make a sub n minus L less than epsilon prime, or less than epsilon over 2, right?
Right.
So I know that, yes, in fact, there does exist an epsilon prime such that n, as long as little n is bigger than epsilon prime, then it will certainly be the case that a sub n minus L is less than epsilon over 2. By the exact same argument, I know that I can always find some n double prime such that as long as little n is bigger than n double prime, it will certainly be the case that b sub m minus m is less than epsilon over 2. Right? And then we would win, right? Because over here I get epsilon over 2, over here I get epsilon over 2, and that's exactly what we wanted, was to make sure this thing on the right was epsilon, which forced this thing on the left to be smaller than it.
Mm-hmm.
Okay,
Awesome.
but now here's another potential pit. Here's another little problem we need to deal with. Just a tiny little problem. So what do I pick n to be? Right? I know that if I take n, I know that if I take n prime, it will make sure that a sub n minus L is epsilon over 2. And I know if I took n double prime, it would make b sub n minus m less than epsilon over 2. But I want both of those things to be true at the same time, right? And
Mm-hmm.
n prime and n double prime, those could be different numbers. Because
Right.
a sub n and b sub n are just two random sequences, right? One of them you might need to go a lot further along before you're in the epsilon over 2 ball, right?
Right.
So
Hmm.
how could I choose an n that I know would make both of these things true? I know that if I at least choose n prime or anything bigger, and I at least choose n double prime or anything bigger, I'll get what I want. Well, in each separate case, I want both of those things to be true at the same time.
Could you just say n plus 1 or something? It needs to be something bigger than n.
Well, it needs to
Or
be something bigger
hmm,
than or equal to,
n primed.
and bigger than or equal to
Ah, um, well, if it needs to be bigger than or equal to those two, can you put them together? That
Sure. How are you going
just
to put
add them together?
add them together? Yeah. Yeah, exactly. So
Right. Okay.
we could choose n to be n plus n double prime. And that will work. Exactly.
Okay.
What you typically might see in a textbook, just because sometimes we like the more efficient, this will do the job, this will get the job done, but you'll sometimes instead see mathematicians choose this. Instead, they'll simply write max
Hmm.
n prime n double prime, which just says take the largest of the two, right? Because let's say n double prime is bigger, right?
Sure.
Well, then certainly if you choose n double prime, this will be true. But also, since if n double prime is bigger, and we know if it works for some n, it'll work for all those bigger n, well, then certainly we'll make the other statement true as well.
Okay. So just take the larger of the two. So the
Yeah.
max, you've basically got a couple of them. It's a set,
Mm-hmm.
and of that set,
You just make
then
sure you pick whichever of the two is the largest. Yeah.
sure.
Yeah. So I just wanted what you said is awesome. You can take their sum. That will definitely work. That will definitely get the job done. I only mention this writing it as a max because that is common in mathematics and analysis to use the max here.
Okay.
But we can do the proof with your choice. With writing it as n prime plus n double prime. So we haven't done the proof, right? What we've done over the last like 20 minutes or so is we came up with a really, right? Things are messy. Look at the screen. There's crap all over the place, right? We did some experiments, some playing around, some digging, and we sort of found the essential ingredients. But now it's time to get poetic. You want
Hmm.
to you know, now we want to write a nice argument, right? If you just emailed this picture to a friend and said, oh, look, I proved the sum of the limits is the limit of the sum, their eyes would pop out of their goddamn head, right? Like, this is incomprehensible, right? Now we want to write a nice piece of mathematics that explains to someone who's happened upon this document exactly how to go about this, right? So let's work on writing the proof now, right? So proof. Okay. So if we go back to our definition, right, up here, this is the thing that we're ultimately trying to prove, right? This is the statement that we're after. And the beginning of this says that for any epsilon bigger than 0, right? So this says you need to give me a recipe based off of any arbitrarily chosen epsilon. So let's begin by choosing an epsilon, right? So proof, let epsilon, be a rational number such that epsilon is greater than 0. Right?
Sure.
And now, so what's the next thing we need to do? Well, we need to choose our n. We need to specify at least one n, convince the reader there is such an n, such that all the rest of this nonsense is true, right? But we found that n, right? We worked backwards. We already did the rough work, right? How did we pick that n? Well, first off, we needed, it actually depended on getting two other n's first, right? An n prime and an n double prime. So let's formally argue why we know those n and n double prime exist in the first place, right? So let's remind the reader why we can pick that, right? So we might say something like, since we're assuming right? So it's good to, right, instead of just pulling facts out of thin air, right? You might have it clear in your head. Oh yeah, that's part of our assumptions. Remind the reader what our assumptions are, right? We're assuming that the limit of a sub n is equal to L, and the limit of b sub n is equal to m. So since we're assuming that, and moreover, it's also helpful to say, epsilon over 2 is bigger than or equal to 0. Since we're making these assumptions, by definition, there exists n prime and n double prime. Maybe let me write it this way. There exists n prime and n double prime in the natural numbers such that n bigger than n prime implies a sub n minus L is less than epsilon over 2, and little n bigger than or equal to n double prime implies that b sub n minus m is less than epsilon over 2. Right?
That's the statement.
That's the statement, right? So all we've done so far is we've reminded the reader, we've said, hey, we've got these assumptions about the limits of a sub n and b sub n, and we haven't just said, oh yeah, I can find an n prime and an n double prime that does this. We reminded them, we said, hey, this is actually what the definition of a limit says, that it says that I can find an n prime that does this and an n double prime that does that, right?
Mm-hmm.
Okay, so now let's get on to the thing that we actually want to show, right? So we might even add in an extra sentence, right? Therefore, taking n defined to be n prime and n double prime, and we're about to use the triangle inequality. So let's let the reader know that that's what we're doing, so they understand the next line of what we're about to write. And how do I know we're doing the triangle inequality, right? So I should have done this earlier. Let's go back to our checklist. So we took some abstract epsilon that we fixed. We also cooked up some recipe for an n in the natural numbers, right?
Mm-hmm.
Now the last thing we need to do is to suppose that a little n is bigger than or equal to the n that we cooked up, and show that this thing is less than epsilon, right? So by the triangle inequality, if little n is bigger than or equal to n, well, what's the thing that we want to show is less than epsilon? It's a sub n plus b sub n minus L plus m. That is equal to, I would personally, this is just my style of writing mathematics, to make it a little bit easier on the reader, I would take one extra step to rearrange the equation first. So I would write this as a sub n minus L plus b sub m minus m, right? So even before I apply the triangle inequality, I'm just rearranging things so that you can see, okay, step one, all I did was rewrite the order these symbols appear in, so that it's a little bit easier when I go to write the triangle inequality that you see, yes, that's exactly what I'm doing there, right?
Mm.
It's just I made it two separate steps, so it's a little easier to digest each piece of the argument. Personal preference about how to conduct this. Okay, and now the next step is, well, we've already argued that both of these things are separately less than epsilon over 2, right? So this is epsilon over 2. This is epsilon over 2. And that is equal to epsilon. Now, our story needs a denouement, a falling action. The climax has happened, right? The most exciting part. We showed that this thing up on the left is less than epsilon. That's the thing that we needed to show by definition. So let's say that. Let's wrap the story up and say something to the effect of thus. We have shown by definition that the limit as n goes to infinity of a sub n plus b sub n is equal to L plus m, which is the limit of a sub n plus the limit of b sub n.
Awesome.
And that's where we would end the proof.
Well, that's going through this with you has made this clearer, and now we have it so I can rewatch it and digest it. And I think it's worth noting, because when you and I were speaking before, as it may have become apparent to other people who will watch this, my algebraic skills are just in development. I haven't done algebra in many years, so I'm just trying to get back into doing maths. And so we recommended these books, and I've started reading them, and I'm really enjoying them. And despite not being proficient with calculus or even algebra, we're able to make sense of these what seem to be higher level ideas in mathematics, and it's really feels really rewarding. And I just want to communicate that to you and to everybody who watches this, that this has become kind of my life. On the bus, I read about math now, and it makes the day go by, and I really enjoy it. It's awesome.
Awesome. I've got another impressionable young man hooked on mathematics.
Yeah.
My plan is coming together. Yeah. Well, I'm so glad to hear it. And well, I think I think that we're at a good stopping point for today's episode. So again, I guess we didn't end on a particular homework problem. Let me say this. So I wonder, do I want to tell you facts about limits and then have you go look up their proofs? No, here's what I'm gonna say. So homework one, what other properties do you expect to hold for limits?
Yes, I have an idea.
Right? So well, what's your idea?
Well, if we're looking at basic operations, then the product of two limits,
Right? I mean,
should be the same.
Yeah, we just checked that the sum of two limits is the limit of a sum. Seems like probably products and like basic stuff we can do with numbers like that. Seems like that should also be the case, right? Seems like it should also be like it should respect products. Think about other things, right? Take a little bit of time, ask yourself what possibilities could there be, right? So first, think about all that you might hope to do with limits of sequences, and think about what the answer is going to be.
Okay.
Number two, and let me give you fair warning, some of these other things are harder to prove. They are harder to prove, but think about their proofs. Right? More important than getting the solution. If you get the solution, I mean, that's what I want you to do. Get the solution if you can. But even more important than getting it is thinking about it, right? See if you can get the solution. Just struggle with it, right? get stuck, right? Get confused. That is important, right? So think about the proofs. After, and by the way, this goes for everyone who's watching at home, right? If the people are still following the series, all of this goes for you too, right? You gotta, if you're cheating these homework assignments, you're only cheating yourself, right? So think about the proofs. And then number 3, only after you've dreamt about what could be true for limits, and you've done your own thinking through what the proofs might look like, only then I want you to then Google it, right? So look up things about limits, right? So you could look at Google. There's also a website called Math Stack Exchange, where people ask each other questions and answer questions about math and higher level math. Think about these things. Find other properties. See if you can find something about limits that you didn't think would be true, or that you didn't think of. And look at some of the proofs too. Try and prove things on your own. But if you get stuck, like, look at how someone else proved some theorem about limits.
Okay.
Yeah.
And may I ask, can you think of one other example that you'd be willing to offer regarding properties of limits besides the really elementary one that I offered?
Yeah. Well, yes, but some of them. I mean, here's a stupid one. So you talked about products of sequences, right?
Mm-hmm.
What is there? Addition, multiplication.
The difference of.
Yeah. But that's it's a little bit dumb, right? Because right, adding the sequence b sub n minus b sub n. This is the same thing. Oh, maybe it's not so dumb, actually, right? So this is the same thing as adding the sequence a sub n and minus b sub n. Right? So actually, this comes out of the addition property. But let me give you a big fat warning. If you just try to do this with division, something could go wrong. You need to be very careful. Anytime there's division, you need to be very careful, right? Because there's something you can't divide by.
Right.
So
Gotcha.
Careful about that. But actually, this brings us to a good point, right? Like we don't want to take anything for granted. And this leads us to a second guess, right? You would also think that this should be true, and actually this would come out of the product law, right? Using constant sequences, this would actually come out of the product law. But if the limit of b sub n is L, then it should be the case that the limit of minus b sub n is
negative L.
Negative L. See if you can prove this. If you understood today's proof, you should be able to come up with the proof of this on your own. It shouldn't be too much more difficult. But this is something you should prove. I mean, it would follow if you do. So I think this you could prove. It would follow from the product rule for limits, but that's going to be a more complicated proof. But just this version of it, you could prove on your own. And
okay.
But this just shows you, right? All these simple things. It seems like such a simple, obvious thing, but we can't take it for as given, right? We need to check. We want the proof. We don't actually know that that's true yet, right? So you need to come up with a proof before you can use this property. And then once you use this property, you could, for example, use it in this to prove that the rule about differences of limits follows from the rule of sums of limits, for example.
Right.
Yeah. So I think that's it for today. Thanks for joining me. Thanks everyone at home. Please don't forget to, ask questions in the comments, make some mistakes, and get confused. And we'll see y'all next week, I hope.